All right, Unit 6, Lesson 6, Exponential and Logarithmic Functions. So our lesson essential question is, how do properties of exponents and logarithms help you solve equations? At the end of this lesson, you'll be able to solve exponential and logarithmic equations. Concept: property of equality for exponential equations. So in symbols, suppose b is greater than 0 and b can't be 1, then b to the x equals b to the y, if and only if x equals y. If two powers of the same base are equal, then their exponents are equal. If two exponents are equal, then the powers with the same base are equal. Example 1, solve exponential equations using a common base. So what is the solution to 1/2 to the x plus 7 equals 4 to the third x power? So I write the original equation, and I rewrite each side with a common base. So in this case, a common base of 2. Okay, so because 4 is 2 squared, 1/2 can be written as 2 to the negative first power. So by the power of a power property, this becomes 2 to the negative x minus 7 equals 2 to the 6x. So that means because they have the same base, their exponents have to be equal. So negative x minus 7 equals 6x. Then I add x to each side, and then divide both sides by 7. So that means x equals -1. All right, so let's try it. Solve each equation using a common base. I have 25, 3 to the x equals 125x plus 2. So the first thing that I want to do is rewrite 25 and 125 so they have a common base. So 25 is 5 squared, and 125 is 5 cubed. And I can apply the power rules. So when I'm raising an exponent to an exponent, I multiply them. So this is really 5. 2 times 3x is 6x equals 5 to the 3x plus 6. Okay, so since they have the same base, I can set their exponents equal to each other. Subtract 3x from both sides, so I get 3x equals 6, and then divide both sides by 3, so I get x equals 2. B is 0.001 equals 10 to the 6x. Okay. So 0.001 can be written as, let's see, 1, 2, 3, 4 as 10 to the -4th equals 10 to the 6x. So -4 equals, no, that's not right. Not 4, this should be 3. Okay. So then -3 equals 6x, divide both sides by 6, so x equals -1/2. All right, example 2, rewrite exponential equations using logarithms. How can you rewrite the equation 17 equals 4 to the x using logarithms? Okay, so there's no common base for 17 and 4. So I write each power as a power of 10. So 17 equals 4 to the x. So writing each using the power of 10. So I have 10 log 17 equals 10 log 4x. So that means log 17 equals log 4x by the power of equality for exponential equations. So rewriting expressions using logarithms can help you solve many types of problems. All right, so let's try it. Rewrite the equation 5 to the x equals 12. So again, neither of these have the same base. Like there's nothing that I can do to 12 to get it to be 5. There's nothing I do to 5 to get it to be 12. Okay, so I can rewrite this as powers of 10. So similarly to, I'm going to write this as 10 to the log 5 to the x equals 10 to the log 12. Okay, by that, I can say log 5 of x equals log 12. So basically I'm putting log in front of each of these. Concept, property of equality for logarithmic equations. If x is greater than 0, then log base bx equals log base by if and only if x equals y. If two logarithms, exponents, of the same base are equal, then the quantities are equal. If two quantities are equal and the bases are the same, then the logarithms or exponents are equal. So basically, this property of equality goes for exponential as well as logarithmic equations. Example 3, solve exponential equations using logarithms. So what is the solution to 3 to the x plus 1 equals 5 to the x? Okay. So I'm going to write the original equation, then I'm going to change it to a logarithm using the property of equality for logarithmic equations. So log 3x plus 1 equals log 5x. Okay. I use the power property of logarithms to bring the x plus 1 down to the front and this x down to the front. Okay, so now I can use the distributive property. So I have x log 3 plus log 3 equals x log 5. I move terms and factor out the x. So I have x times the quantity log 3 minus log 5 equals negative log 3. Then I divide to solve for x, and then I substitute all of this into a calculator, and I get approximately 2.15. Okay. You can always double check by substituting 2.5 back in for x and solving. So when I put 2.5 plus 1 and I raise that to the third from the third, so third plus whatever that is, it should equal the same thing as 5 raised to the 2.15, or close enough. All right, let's try it. Write the solution to 2 to the 3x equals 7 to the x plus 1. So I'm going to say log 2 to the 3x equals log to the 7 x plus 1. Okay. So I can bring that 3x down front. So I have 3x log 2 equals x plus 1 log 7. I use the distributive property. So then I'm going to solve for x. So I'm going to bring 3x log 2 minus x log 7 equals log 7. Factor out an x, so I have x, 3 log 2 minus log 7 equals log 7. So x equals log 7 divided by 3 log 2 minus log 7. Okay, then I'm going to substitute that into my calculator. And that is going to give me 14.57 approximately. All right, example 4, use an exponential model. The diagram shows how a forest fire grows over time. The fire department can contain a 160-acre fire without needing additional resources. About how many minutes does it take for a fire to become too big for the fire department to contain without additional resources? Round to the nearest minute. Okay, so we can see that 4 acres, t equals 0 minutes. And as it grows, it's 7.22 acres at t equals 1. At t equals 2, it's 12.96. And at t equals 3, it's 23.3. So the first thing I want to do is formulate, because the ratios of the number of acres from the diagram are all 1.8. Okay, so I go 4 to 7.2 to 12.96 to 23.3. Okay, they're all 1.8. And we got that by taking 7.2, dividing it by 4. So this one, 12.96 divided by 7.2 also gives me 1.8. So that's how I'm getting that. So each time I'm multiplying by a factor of 1.8. So the exponential growth model uses b equals 1.8. Use the model y equals ab to the t power, where y represents the number of acres, a is the initial number of acres, b is the growth rate of the fire, and t is the number of minutes the fire has raged. So they said that they can handle a fire that's up to 160 acres. So 160 acres equals 4 Okay, so that's the initial number of acres that they used, was 4. So here's 1, 2, 3, 4 acres. Okay. Times 1.8, which is the growth of the fire, to the t power. Okay, so now I'm going to compute. I solve the equation for t. So 160 equals 4 times 1.8 t. So I divide both sides by 4 to get 40 equals 1.8 t. Then I take the log of both sides. So I have log 40 equals log 1.8 to the t power. I can use the power property of logarithms to bring that t down front. So I get log 40 equals t log 1.8. I divide both sides by 1.8. And that gives me my value for t. So 6.276 is approximately t, what t value is. Remember that t represents time in minutes. So I verify the answer by evaluating the expression 4 times 1.8 to the 6.276 power, which gives me approximately 160. Okay, so the fire department has a little more than 6 minutes to contain the fire before they will need additional resources. So the diagram shows how a forest fire grows over time. The fire department can contain a 160-acre fire without needing additional resources. About how many minutes does it take the fire to spread to cover 100 acres? Okay, so this is the same exact factors that we were given. I want to know how much time it will take the fire to get to 100 acres. So 100 is going to be my goal, equals 4, which is the original amount of acreage that we're looking at, times 1.8, the amount of time that the fire spreads each minute, to t. So just like we did in the previous example, I'm going to divide both sides by 4. 100 divided by 4 is 25, equals 1.8 t. From here, I'm going to take the log of both sides. So log 25 equals log 1.8 t. Okay, I can bring that t down front. So log 25 equals log 1.8. I divide both sides by log 1.8. So I get log 25 divided by t equals log 25 divided by log 1.8. And when I put that into my calculator, t is approximately 5.5. Okay, so this means that it will take approximately 5.5 minutes for the fire to cover 100 acres. All right, example 5, solve logarithmic equations. What is the solution to ln x squared minus 16 equals ln 6x? All right, so ln x squared minus 16 equals ln 6x. So I rewrote the original equation. Okay, so I can use the property of equality for logarithmic equations, which tells me that they have the same base. So that means x squared minus 16 equals 6x. I'm going to move the 6x to my left-hand side and set up a quadratic equation, which equals 0. Here I can factor it, which is great. We love to be able to factor. Makes our lives a little bit easier. Of course, you can complete the square. You can also use the quadratic formula, whichever way works the best for you. Okay, so when I factor, I get x minus 8 equals, or times x plus 2 equals 0. I solve both of these for x, so I get x equals 8 or negative 2, and then I check. Make sure that you check because you may have an extraneous solution on your hands. So I substitute each value into the original equation, x equals 8, which does work. It gives me ln 48 equals ln 48. Okay. I also substitute in negative 2. I get ln negative 12 equals ln negative 12. But I can't have a negative value here for ln. It doesn't work. So because logarithms are not defined for negative values, only x equals 8 is a solution. The value x equals negative 12 is an extraneous one. All right, so let's try it. Solve each equation. Log base 5 x squared minus 45 equals log base 5 4x. Okay, because I have the same log to log base 5, I can set these equal to each other. So I have x squared minus 45 equals 4x. I'm going to move the 4x to the other side. So I get x squared minus 4x minus 45 equals 0. Now, I'm going to see if I can factor 9 and 5 would give me 45 and 4. So x minus 9 and then x plus 5, 0. You can, of course, double check x minus 9 times x plus 5 and make sure that it does work. Negative 9 times 5 gives me negative 45. Negative 9 plus 5 would give me negative 4. Okay. So then my answers are x equals 9 or x or negative 5. Double check both of these. So log base 5. We'll do 9 first. 9 squared minus 45 equals log base 5 of 4 times 9. Log base 5 of 81 minus 45. 36. So log base 5 of 36 does equal log base 5 of 36. Okay. Okay, that one works. 9 works. I have to check my other one. So I have log base 5 of negative 5 squared minus 45 equals log base 5 of 4 times negative 5. Okay, so this gives me 25 minus 45 equals log base 5 of negative 20. I can tell right now I have negative 20. I can't evaluate a negative log. It just doesn't work. So that negative 5 is going to be an extraneous solution. So 9, so x equals 9, negative 5, which is extraneous. For B, I have ln negative 4x minus 1 equals ln 4x squared. So again, I can set these equal to one another. So I'm going to solve, I'm going to move all of my numbers and variables to one side so I can set up a quadratic. This gives me, okay, so 2x plus 1 times 2x plus 1 equals 0. So x equals 2x plus 1, subtract negative 1/2. Since it's 2x plus 1 squared or 2x plus 1 times 2x plus 1, I get x equals negative 1/2. So there's one answer. Okay, I'm going to double check, make sure it works. Negative 4 times negative 1/2 minus 1 equals 4 times negative 1/2 squared. Negative 4 times negative 1/2 gives me 2 minus 1. And then negative 1/2 squared is negative 0.25. So 4 times 0.25 or 1/4. 2 minus 1 is 1. 4 times 1/4 is also 1. So they do work. So x equals negative 1/2. All right, example 6, solve logarithmic and exponential equations by graphing. What is the solution to log 2x plus 1 to the 5th equals x minus 2? You can use the graphing tool to explore the points of intersection of the function. First, rewrite the left side of the equation using the power property of logarithms. So let y sub 1 equal 5 log 2x plus 1. Okay, so I just moved that 5 down in front. And y sub 2 equals x minus 2. I graph both equations and I find the point of intersection. They happen to have 2 points of intersection at negative 0.329, negative 2.329, and at this point up here, 8.204, 6.204. The the points of intersection to the nearest thousands. I double check those points. So I let x make sure that they're equal. So they both work. The solutions are x is approximately negative 0.329 and x is approximately 8.204. All right, so let's try it. Solve the equation by graphing. Round to the nearest thousand. So I have 3 times 2 to the x plus 2 minus 1 equals 3 minus x. Okay. So I can write them in here. So I have y equals 3 times 2. Okay, so there's my two functions. 3 times 2 to the x plus 2 minus 1. I had to put this in parentheses. And then I have 3 minus x as my second equation. Okay, I can see here, scroll out a little bit, that they intersect here at one point. Scroll in, make it a little bit easier. There's my point of intersection, or approximately my point of intersection. So I have negative 1.205 and 4.205. So that means x is approximately negative 1.205. All right, so let's try it. Solve the equations by graphing, round to the nearest thousand. So I have ln 3x minus 1 equals x minus 5. So again, I can just substitute them in. Y equals ln 3x minus 1 and y equals x minus 5. Here's my two equations. Here, there's 2 points of intersection. So I have one down here at 0.336, negative 4.664, and 8.156, 3.156. Okay. So x is approximately 8.156, or x is approximately 0.336. So the nice thing with Desmos is you can enter it in exactly how it's written. You don't always necessarily have those options on a calculator, but Desmos does allow you to do that. Concept summary, exponential and logarithmic functions. So we have the property of equality for exponential equations. If b is a positive number other than 1, b to the x equals b to the y, if and only if x equals y. So if two powers of the same base are equal, then their exponents are also equal. And if two exponents are equal, then the powers with the same base are equal. So if 2 to the x equals 2 to the 4, then x has to equal 4. If x equals 4, then 2 to the x equals 2 to the 4th power. You also have the property of equality for logarithmic equations, which is almost the exact same thing as the property of equality for exponential equations, except you're dealing with logs. So if b is a positive number other than 1, log base bx equals log base by, if and only if x equals y. So if two logarithms of the same base are equal, then the arguments are equal as well. If two arguments are equal, then the bases are the same. Then the logarithms are also equal. So if log base 3x equals log base 3, 8, then x has to equal 8. In the same vein, if x equals 8, then log base 3x has to be log base 3, 8. And that is the end of Unit 6, Lesson 6.